So today we want to go a bit deeper into this LDPC decoding. And we already started last time by deriving a measure that is typically used in these decoders, the so-called log likelihood ratio. And let me start again by briefly reviewing what we actually did there, how this LLR, log likelihood ratio, is defined. This is basically what we did last time. So this log likelihood ratio basically describes the probability with which a certain observed value, we called it here y0, resulted from a plus square root EB that was transmitted or from a minus square root EC that was transmitted. So we can basically calculate these two probabilities here. So notice, of course, if we observe a value here, a positive value, like we've drawn it here, the probability is quite a bit higher that a plus 1 or plus square root EC was transmitted as if a minus square root EC was transmitted. But also notice it could be that we transmitted like a -1 and the noise was so big that we receive values being larger than 0, which would actually result in a decoding error. But of course, we can also calculate this probability. This would be here the red probability. And the log likelihood ratio is basically the natural logarithm between these two probabilities. So therefore, we basically had to calculate these two probabilities first. What we basically did here, just setting in the Gaussian distributions from our noise process here. This is what we find here, and simplifying this, which at the end gave us this result for the log likelihood ratio. Well, of course, it depends on the value that we receive here, at the value y, and the energy per coded bit at the receiver. Actually, this will influence this log likelihood ratio, and of course the noise variance. So also note here, the log likelihood ratio will become smaller as the noise variance increases. So the more noise we get, the more unreliable will be our observation. Yes, and here the simplified case, if we normalize our received bit energy to 1. So actually there was a small mistake on the lecture slides, but I corrected this. So for the next turn, we will have the correct equations there. But well, on the board, on the writing, you have everything correct. Okay, then we made an example looking at the 7,4 Hamming code, normalizing the energy per coded bit to 1. Then we have an energy per bit, of course, which is larger due to the redundancy. So we've talked about this before. We assumed we have a certain signal to noise ratio. Here I wanted to use just 5 dB for our example on a logarithmic scale. On the linear scale, this turns into 3.16. And with EB known from up here, 1.75, I can calculate N0, so the noise power spectral density. And with N0, I can calculate basically the noise variance. So these are basically the numbers that I would need to come up with a simulation, calculate this log likelihood ratio. And then basically just following this example, I assume I transmit a 1 bit. This is mapped to minus square root EC. As we normalize this to 1, it's mapped to -1. Our noise sample, which comes basically from a Gaussian distributed random variable with the noise variance given as described here. Assume we get just a value of 0.2 from this random process. Then what we observe at the receiver will be this -1 plus 0.2. So -0.8, this will be the value at the, let's say, correlator output. So the value which we will use for our decoding which we'll use for our decision. And with the values given here and the equations we derived, we can actually calculate the likelihood ratio, which turns out to be minus 5.8 in this case. So large negative values, very safe or very likely that -1 was transmitted. Very large positive values, very likely that a +1 was transmitted. So here we have a fairly big value already. So with a very high probability, if we observe -0.8, actually -1 was transmitted. So here in contrast, we came up with a second example. So assume again we transmit a bit being 1 mapped to -1. Then we have a quite large positive noise sample here, again, from the random distribution, so it could be any value here. But in this case, it's so large that we basically end up with a positive value here at the receiver, which also turns into likelihood ratio, but a fairly small value. So here, from this small value, we can conclude that this is not very safe, this decision. You see, actually, the decision would be wrong. If we say we observe 0.2, probably a +1 was transmitted. Positive log likelihood ratio, probably +1 was transmitted, which is wrong. So this is actually a case where things go wrong, but we will actually deal with this in the Tanner graph and in the LDPC decoding to basically improve this log likelihood ratios over several iterations and actually at the end come up with the correct result. But these were just examples to give you a feeling for this log likelihood ratio. So the larger the value, for example, if we would have here a noise sample of 0.01, we would receive a -0.99, then we might get a log likelihood ratio of like -10 or so. So the larger this values are, basically the more safe will be our detection. Okay. So then some more equations. Of course, the log likelihood ratio is a measure between the two probabilities. So is it more likely to be a +1 or is it more likely to be a -1? So this means also if we know log likelihood ratios, we can also calculate probabilities for the observations to result from a +1 or to result from a -1. This is actually what we did here, solving this log likelihood ratio for the probability of the bit to be a +1 or to be a -1. So we can actually calculate probabilities from the LLRs. Also here, following our example, if we have a log likelihood ratio of -5.8 from before, and I use these equations to calculate the probabilities, we can say with 99.7% probability, this observation resulted from a 0 bit that was transmitted or mapped to +1. It could have also resulted, so this observation could have also resulted from a -1 that was transmitted, but only with like 0.3%. So, or the other way around, let's explain this again. If I observe a value of -0.8 at the receiver, if I observe 1,000 times this value, 997 times, it will result from a 1 bit that was transmitted, and only 3 times it will result from a 0 bit that was transmitted. Only 3 times we would have such a large noise amplitude that we end up with the same log likelihood ratio. So important here, log likelihood ratio, a measure for the probability that our observation looks more like a +1 bit or like a -1 or 0. Okay, so are there questions so far regarding the log likelihood ratio? Okay.
Sir,
So
mapping has to be done always with +1 and -1. There is no other means coding strategy that we can follow.
well, let's say this is, of course, the most easy one. So you can also define log likelihood ratio, for example, for higher order modulation schemes where you have something more difficult as this just binary mapping to +1 and -1. But then also this log likelihood ratios become a bit more difficult.
Okay.
So
to make our calculations convenient, we have gone for +1 and -1.
Yes.
Okay. Okay.
So we consider the most simple modulation scheme like a binary bipolar modulation.
Okay.
Whereas, of course, you could also consider all other modulation schemes at the point where you have the signal demodulated, like to 0 and 1, and you map these values to + and -1. So also more complex modulation schemes could be considered. But then things get a little bit more difficult regarding the log likelihood ratios. But it's a good point. Let me make a note that I tell you at least how you could deal with log likelihood ratios in higher order modulation schemes. I think that's an important question, actually.
Like M array means when
Yes,
okay.
Exactly.
Okay. Thank you, sir.
Okay. So let's see what we want to do today. So today we need some more theoretical result in order to come to the actual decoding of these LDPC codes. Again, prerequisite. We will see that at a certain point we need to know the probability that a sum of certain binary random variables will turn out to be 0 or will turn out to be 1. So probability that a sum of binary random variables will be 0. Or we could also ask the other way around, what's the probability that the sum will be 1? But to get started, we ask for 0 here. So assume B1 and B2 are binary random variables, and we ask for the probability that B1 plus B2 is equal to 0. Binary random variable. Well, what can happen? Can be 0 plus 0, can be 0 plus 1, can be 1 plus 0, can be 1 plus 1. So in this case, sum will be 0. In this case, the sum will be 1. Here the sum will be 1, and here the sum will be 0. Now we need to one more definition. So for example, the probability that B1 is 1, we call this Q1. and the probability that B2 is 1, we call it Q2. So those are our probabilities. So let's see when this turns out to be 0. See, in the last case, if B1 is 1, B2 is 1, and this will happen with probability Q1 times Q2. So this refers to the case 1 plus 1. But the result of the sum will also be 0 in the first case. So if both bits are 0, and this will happen with probability 1 minus Q1 times 1 minus Q2. This will be the probability for the case that both are 0. Well, I think this is not too difficult, but we want to extend this further then on an arbitrary number of bits. This will be a bit more difficult. And therefore, I bring this to a special form. So let's basically multiply this out. Q1 times Q2 plus, so what do we get here? 1 minus Q2 minus Q1 plus Q1 Q2 . Actually, these two guys can be, of course, combined. So this is 1 minus Q. Let's rearrange this Q1 minus Q2 plus 2 Q1 Q2 . And the last step is maybe not so easy to see. Let me write it down and then explain it. 1/2 times 1 plus 1 minus Q2 Q1. So it has a special purpose why I bring it to this form, 1 minus 2 Q2. Notice if you multiply this out here in the brackets, you get 1 minus 2Q2 plus minus 2Q1 with this factor 1/2. We get these two guys. And at the end, we have minus 2Q1 times 2Q2. This is 4 Q1 Q2 times 1/2 is this one. So this is equivalent. So let's write this again. So this is the probability that B1 plus B2 is equal to 0. And just as shorthand notation, I call this Q. Shorthand notation. For later use. And of course, it's straightforward to extend our example a little bit. By asking what's the probability that the sum of three guys we know this from before. So this will be 0 with probability Q. Or it will be 1 with probability 1 minus Q. So with probability 1 minus Q times Q3. This will be again the case that B1 plus B2 is 1 actually, and Q and B3 is 1. So this would be the case 1 plus 1. Result will be 0. Or the case where both are 0. So with probability Q, B1 plus B2 is 0. And with probability 1 minus Q3, yes, 1 minus Q3. Basically, the bit 3 will be 0. So this will be the case where we have 0 plus 0. Then again, we can multiply this out. So this will be Q3 minus Q3 plus Q minus Q3. Or Q plus Q3 minus 2Q3. Now basically this derivation is a bit tricky, so there I would refer you to the lecture slides. Maybe you also find a smart way how to do this a bit more briefly. See lecture slides. But at the end, I can bring this again to a form 1/2 plus 1/2 times 1 minus 2Q1 1 minus 2Q2 1 minus 2Q3. So this actually really becomes a nice equation. Even though the derivation is a bit lengthy, but at the end, if you think a while about it, you will see that you can actually bring it to this form. So the probability that a sum of, let's say here, n binary values will be 0. So probability b1 plus b2 plus bn 0 is 1/2 plus 1/2 times the product. So we get n times this expression now, I being 1 up to n, 1 minus 2 qi. So this is an equation that you will often see when LDPC codes are treated, because we will see that we need this kind of equations when we try to gain some information on one specific bit from all other bits. But we will see this today. Or actually the other way around. We could also say, let's write this here, PB1 plus Bn I could also ask the other way around, what's the probability that the sum will be 1? Of course, this will be 1 minus the probability that the sum will be 0. So I could also say here P B1 plus B2 plus Bn is 1. So what's the probability that the sum will be 1? It will be 1 minus this one. So 1 minus 1/2 is 1/2. And yes, and minus 1/2 times the product I being 1 to n, again 1 minus 2 qi. So those are important equations. That we will need later on. Okay, now we basically know enough to actually see how the decoding works. So let's see, we come to the suitable example. So now the decoding. And in order to understand this well, we want to start again with the 7,4 Hamming code, treating this as if it was a good LDPC code. So this means we have our 3 check bits or check nodes. We have 7 so-called bit nodes. And let's draw the link. Use less bright color here. So we have the first bit going to the first check node, second, third, and the first parity bit going in here. Then for the second check node, we have the second, third, fourth, and second parity bit here. And for the last one, we have the first, the second, and the fourth. And the last parity bit here. Yes, of course, we again look at the 7,4 Hamming code, e.g. 7,4 Hamming code. It's not right. Hamming code. And we need to introduce some more variables here. So first of all, we need an index on this check nodes. We call this index J. Which is like the index of check nodes. And of course, we also will need an index for the bit nodes, all this I. 2, 4, 5, 6, 7. The index of bit nodes. And I will start explaining this by explaining it with using the probabilities, because this is still a bit more intuitive as the log likelihood ratios. So we will have some other index, I prime, and we will have some intrinsic information. Let's call this P int of I prime. Okay, so let's look at a first example. Basically, I want to ask the question, what can we conclude on bit node 3 by using all the other bits and how they are linked along check node 2. So basically the question is, so let's see which bits are linked here. So this one has a link to check node 2. This one has a link to check node 2, and this one. So the question is, what information on bit node 3, so on observation 3, can we get from knowing the observation of these values here and knowing that at the end, if the sequence will be a correct sequence, the check node needs to be 0. So this we know. So at the end, the sum of all the bits linked to this check node must be 0. And I can use this condition basically to get information on this, let's say, observation 3. So let's try to write this in a sentence. So what information on bit node 3, can we get from check node 2 comma using the other observations which are linked to check node 2. Yes, and this is actually how we, or why we have this additional index I prime here. In this I prime, I only consider the indices with the nodes being linked to check node 2, 2, 3, 4, and 6. This we call it Bj. Here in our case, B2. So basically, this is the union of the bit nodes being linked to check node J. So check node is. So bit nodes comma linked to check node 2. Check node J, comma here J2. And this P int, this is the intrinsic information. So what do we know about our bits? Intrinsic information. Well, it's more a probability as an information. Probability that bit I prime is a 1. So I think I also came up with an example with numbers. Just a second. Yes, let's use this one here. So assume we have here a probability that bit 2 of 0.9, that this bit is a 1, 0.8 for the fourth one, and 0.9 for this one. Just as example. So all these 3 green guys which are linked here over check node 2 with our bit node 2, let's assume for all of them the probability is fairly high that those ones are 1 bits. Okay, so let's see how we basically can continue. Yes, so now basically the idea is, what can we conclude from this observations here, what can we conclude? Over this check node on this one. So additionally, we know that at the end, in order to be a valid code word, we need a 0 here at the check node, because if we have a valid code word, all the check nodes will be 0. So this is basically the constraint that we know. And with this, we can basically ask the question. So what is the probability that check node 2 is satisfied? So what's the probability that check node 2 is satisfied? If bit node 3 is a 1. So let me go back to show you this again. Okay, now just look again at this example. So these 3 green guys are very likely to be a 1. So the sum up here will be probably a 1 here, plus 1 here, plus 1 here. Sum of 3 ones is a 1. So in order to get a 0 here at this check node, actually the red guy also needs to be a 1. And this is actually the probability that we are asking now. So what's the probability that a 1 here at this bit node will cause this check node to be 0? In our example, as those ones are probably 1s, then with a fairly high probability, a 1 here at bit node 3 will cause check node 2 to be 0. So in this example, high probabilities here for 1s, we will also get a high probability that bit node 3 must be a 1. So satisfied. In our example, we have bit nodes 2, 4, 6. Two, 4, 6 are likely to be 1. So we have the sum of 3 ones. So with a high probability, a 1 at bit node 3 will cause the check node to be fine to be 0. With a high probability, a 1 at bit node 3 will result in check node to be 0. And here we will actually need the equation that we derived. So what's the probability that the sum, let's go back. What's the probability that the sum of these 3 green guys turns out to be 1? Let's see how we call this here. We call it P extrinsic. We'll also tell you what is the difference between the extrinsic and the intrinsic. 2, 3. Maybe let's start with the explanation. Extrinsic information i.e., this means what information can we get here over check node 2 for bit node 3 using all other bit nodes being linked to check node 2. Okay, let's use also some colors that we had before here. So we are interested in bit node 3. And of course, all the bits are linked to this over check node 2. And it's called extrinsic information because we use all other bits, all other bit nodes, but not the bit node itself. So let me go back one slide. Let's write first. So of course, we will also have here an observation of my bit node 3 and the probability of my bit node 3 to be a 1. But notice we don't use this here. I just want to know what can we tell about bit node 3 from the observation of the other bits. So I want to get extrinsic information on the bit that I'm currently looking at. And I get this extrinsic information from these observations, from these probabilities for our observations. I can extract information on my desired bit. Okay, so this is what we want to know. So what's the probability that the sum of these 3 green guys turns out to be 1? And this is what we derived before, 1/2 minus 1/2 times the product So now we need to be a bit careful in this product. Maybe this is on the first view a bit difficult to understand. For I prime being element of B2, but I prime being different from 3. So basically this means I prime element B2. These are actually the green links in the drawing before. So B2 are all bit nodes with a link to check node 2. So we use all of them, just not the one we are interested in, just not 3. So just go back to the drawing. So we somehow need all the links to check node 2. But in order to get this extrinsic information for bit node 2, we only consider now here the green ones. So from this union B2, only the elements 2, 4, and 6. Maybe we could also make arrow here using all other bit nodes. This would actually fit well to this one. And here, of course, in the bracket goes 1 minus 2p intrinsic I prime. So the probability that bits or bit nodes, so which were the ones 2, 4, and 6, okay, and actually for this example, I also calculated the numbers. So this will be 1/2 minus 1/2 times 1 minus 2 times, so what did we have? We have 0.9 times 1 minus 2 times 0.8 times 1 minus 2 times, and again 0.9. In this example with our values, this turns out to be 0.884. So basically from our observations from bit nodes 2, 4, and 6, we can conclude that with probability 88.4%, bit node 3, bit 3 needs to be a 1. So maybe let's also write this here from the observations. At bit nodes 2, 4, 6, we can conclude that with 88.4% probability, bit node 3 will be 1. Let's go back to look at this again in the Tanner diagram. So actually, we already thought about this before. If these 3 green guys are very likely to be 1 bits here, 90%, 80%, 90%, then notice that the sum of these 3 green guys will be 1. 1 plus 1 plus 1 is 1. So then, of course, also with a high probability, bit node 3 must be a 1, because then we will have the sum of 4 ones here, which would also already fulfill this constraint that our check node must be 0 at the end. So if we have here very likely 1 bits, then from this we can conclude that bit 3 is also very likely to be a 1. And actually, we calculated the probabilities that this will happen. Yes, of course, now in the further steps, you can see we could also have here, of course, we will have an intrinsic probability on our bit node 3 here from the noisy observation. It could be that maybe only with 0.1% probability from our observation, we know that bit 3 is a 1 bit. But the information that we actually calculated now is independent on the observation of bit 3. It's all we get from other bits, but not from bit 3. So we get this information from just looking at bits 2, 4, and 6. So therefore, extrinsic information, so this is information which is not related to our observation of bit 3. This is very important to understand the difference between this intrinsic information. So what do we know on a bit from observing it, observing from the noisy observation? What can we conclude on the bit? Intrinsic information. And the extrinsic information, what can we conclude on a specific bit from the observations of all other bits? So this is the external that we get in contrast to the internal from the observation. Okay, are there questions so far? So if you understood this, you already understood the very basic principle of how this will work. So you can imagine that now we could basically improve this estimate of bit node 3 with this extrinsic information. We can combine it with the intrinsic information that we also get on bit 3 from the noisy observation. So bringing intrinsic and extrinsic information together. So this will result in an improved estimate here on the probability of bit node 3 to be a plus, to be a 1 or a 0. And in this way, we basically can improve all these probabilities down here and using this in like an iterative manner, passing back and forth this information, improving our estimates here. So this is already the very basic principle how this will work. And just it's expressed slightly different. So we thought now in probabilities, typically in practical systems, it will be done by using the log likelihood ratios. And this means we need some more derivations to bring this kind of equations from this notation with probabilities to a notation using the log likelihood ratios. So this will be, again, a bit tedious writing down equations, but we will see at the end it will be useful. So typically, LLRs are used instead of probabilities. So let me write down again the equation that we had. The extrinsic information here between check node J and bit node I. This was 1/2 minus 1/2 times the product. So considering all the bit nodes being linked to check node J, just not the one that we are interested in. And we get here the 1 minus P times 2 times P. So the intrinsic, what we know on our, from the observations of our bit nodes I prime. So again, this is the probability. That a 1 at bit node I causes check node J to be 0. And of course, we can also turn this around. I could also ask for the probability that 0 at bit node I causes check node J to be 0. This will then simply be 1 minus this probability, be Ji external. Of course, we could express it in both ways. So if I know, of course, the probability that a bit is a 1, I know the probability that it will be a 0 will be 1 minus this probability. So this is straightforward. And now we basically bring these two guys in a ratio. We call this AJI and EJI. Just bringing this here in this logarithmic relationship. Or actually, I think I wrote ln before. So I also should look at my lecture slides. So here I wrote log. I think before I wrote ln. So let's write ln here. It's the natural log. Ln of the ratio of the probabilities. So 1 minus PJI external, extrinsic. Divided by PJI extrinsic. Yes, well, and let's just plug in our equations here. It's the ln. So up here we get 1/2 plus 1/2 times this product. Again, the product over all i's element bj, so being linked to check node j, just not the one we are looking at. Actually, I prime being different from I. And of course here, the expression as we already know it, 1 minus 2 pi p internal I prime. Divided by 1 minus, yeah, well, this guy. We still deal with some probabilities here. So I also want to use the log likelihood ratio for this intrinsic probabilities here, for the P in. Also use LLRs for P intrinsic I prime. Let's call those M J I prime. So this will be the ln 1 minus P int int I prime divided by P int I prime. Yes, and now basically what I want to do is I want to get this green guy somehow in here. Get mj I prime in here. And there's actually a nice way how this can be done. Maybe it's not so straightforward or intuitive, but this is how it's usually described if you also look in literature. So there's some relationship used. We use. We know that the hyperbolic tangent is like 1/2 times the log 1 minus x divided by x. That this is 1 minus 2x. Okay, so if we just use instead of x our p intrinsic. We already get something useful. Maybe let's write here from like formula book or math book. Okay, so we apply this to our 1 minus p int I prime divided to p int I prime. This is 1 minus 2 times p int I prime. Oh, here I wrote again the log instead of the ln, so I should be more consistent here. Well, of course. Right, ln. And here we actually see, and it's a tangent hyperbolic. Here, this one is basically the log likelihood ratio of this intrinsic probabilities. It's the mj I prime. So we have the hyperbolic tangent of 1/2 mj I prime is equal to 1 minus 2 times p intrinsic I prime. Probably you could also have derived this as we did it before, calculating the probability from the log likelihood ratio with these exponential functions of the log likelihood ratio. And probably you also find the relationship, how this quotient of exponential function turns into this hyperbolic tangent. Maybe it's even not so difficult to derive, but I use this here like from a textbook. So now here we have the LLR instead of the probabilities. And with this, we get finally an equation which, well, it's a bit lengthy. So with this, we get this EJI, so this extrinsic information for bit node I over check node J as the ln (1/2) plus 1/2 times, again here the product over all I primes element bj, so from all the ones being linked to check node J, just not the one we are interested in. And basically here we had the 1 minus 2 p int, which turns into this hyperbolic tangent of 1/2 mj I prime. Divided by 1/2 minus 1/2. The same product here. I prime element bj for I being different from I prime. And here, of course, the same 1/2 times mj I prime. This is now basically this information on bit I that we can extract over bit node j from all other observations expressed as a log likelihood ratio and using just log likelihood ratios. Okay, are there questions? Okay, so then basically just let me go back to the drawing. Well, now notice that, of course, we do not only get information on our bit node 3 from check node 2, but we will also get some information from check node 1. We're using bit 1, 2, and 5. We can also get some information, some extrinsic information on bit 3. Some more? No, that's it. So we also need to consider what information can we extract along bit node 1. And at the end, we will bring it together here. So what do we get from check node 2? What do we get from check node 1? And what do we know from the noisy observation of the bit? So this is basically the next step. So next, bringing information together. For example, if we have here our bit node 3, notice we have here this link from check node 2, we have something from check node 1. So we basically get here, use the same color as before. We get here a E, 2, 3. So what do we know over bit node 2 from all other observations for our bit node 3? And here, what do we know over check node 1? Again, using all observations being linked to check node 1 for our bit 3. And we actually need one thing more, or we know one thing more. We call it here R3. So this is basically just the a priori LLR of bit 3. A priori LLR from the observation. of bit 3. So intrinsic information. So maybe you wonder why I use here R3 and not P_int 3. This is because this intrinsic probability P_int, this will be updated during the iteration, where R1, this R is basically just the probability, or in this case the log likelihood ratio, before we start iterating. So this is basically just what do we know from observing this noisy bit R3. So, and at the end we get here basically the new or the resulting log likelihood ratio L3 to be R3 plus E13 plus E23. And actually, this is the nice thing about using log likelihood ratios here. If we use probabilities, we would have to deal with products of probabilities, products which will tend strongly towards being 0 or towards being 1, so like 0.00001 and so on. So numerically a bit more tricky, more difficult, or more risky to make mistakes. Whereas here in the log likelihood domain, the product will turn into sums. So here we just need to calculate sums of log likelihood ratios. Or in general, Li will be Ri plus the sum over, let's see, J element Ai E J comma I. Where AI would be again like the union of bits of check nodes having a connection to bit node I. Maybe let's write this underneath here. AI the union of check nodes with a connection to bit node I. And now you already understood basically the first iteration. So at the beginning, we have maybe known that from the observation, we're like with 60% probability, bit 3 is a 1. Then we might know from the observation of the other bits over check node 2, maybe we get the information like with 80% probability, it's a 1. And over check node 1, we get the information maybe with 75% probability, it's a 1. And all this information is now combined here, and now just using the log likelihood ratios instead of the probabilities.
Sir, what is this a priori LLR?
A priori LLR, this is basically the LLR that we get from the noisy observation. So let's write this a priori LLR from the observation of bit 3. So maybe let me show you this on my table with the numbers of the example.
So this bit 3, sir, noisy. That is what you mean to say.
Yes, so let me draw up here this example with the numbers again. So we transmit bits mapped to plus minus square root EC, plus minus 1 in this case. We have some noise and we have noisy observations here. And basically the LLR that we just get from our noisy observations, this would be the R3. Basically, before we do anything else, we already know something about our bit just from observing it. So in this example, R3 would be 2.9. Before we start iterating something or before we start gaining additional information. And you see, of course, this log likelihood ratio, let's go back to the example, of 2.9. So this will be changed. This will increase probably. As from the other observations, we conclude that it is likely that this was a +1. So maybe from combining these two additional extrinsic log likelihood ratios that we get, maybe in the next iteration, we will have already a log likelihood ratio here, sum of maybe 7.8 or something like this. So by using this extrinsic information, our estimate on the bit value will improve, the log likelihood ratio will increase. So we have here another question. Could we also, in place of the sum of the LLRs, use the average? See. So let me see. So we add here the sum. You need to be a bit careful if you want to average this. Well, actually, it wouldn't really change a lot if you use the average. Well, actually, yes. So just imagine you have one case where two check nodes influence bit node 3. So the average would be then 1/2 times the sum of these guys. Whereas if you had an example where 4 check nodes influence bit node 3, you would have here 1/4. So you would basically underweight the cases where more check nodes are linked to a bit node as compared to the cases where only few check nodes are linked. So averaging here would not really be suitable. So of course, if we have more check nodes linked to our bit node 3, we also get more information. And the average would basically reduce this influence. So it would not be good to use an average here. We really want to know all the information that we can gain on our desired bit. So we have some more question here. LLRs computed using noisy received values will be called a priori LLRs. Yes, exactly. That's it. So the ones in our table here, before we start doing anything, those are the a priori LLRs. So notice here, this 2.9, this has no relationship to all the other observations. So we just use these other observations when we talk about the decoding, how they are linked together along the check nodes, what can we extract from these observations here, on our, or what can we conclude on our desired bit that we are looking at. Okay, so this was quite challenging and also a bit difficult today, I guess, but I think you should have understood the main principle so far. We are not done. We need to continue a bit further there, but already, let's say, the first step, how basically information from, let me go back. How we can basically extract new information on the desired bit that we are looking at by using our other observations in terms of probabilities or in terms of log likelihood ratios. So gaining information on specific bits here from using the other observations and from knowing how they are linked together at the check nodes and knowing that a check node 0 actually will be needed at the end to fulfill our parity check equations. And of course, this bit 3 was just one example. Of course, you would start with bit 1. So what can we get? What can we get to know about bit 1 from the other observations? See, they are linked over check node 1 to bit node 1 and so on. What can we gain from check node 3 about bit node 1 using the other bits which are linked to check node 3? So this is basically the main idea, extracting additional independent information on our desired bit from the other bits. Extrinsic information, which basically improves the estimate of our bit, as we've seen here. We know something before our bit, but we also have additional knowledge from the other bits. That's the main message for today. What do we gain from observing the other bits while decoding one specific bit? Okay, are there questions? Otherwise, we will continue there next week. And we also will briefly repeat this again, because I'm aware that this is not so easy to understand. Okay, so then thank you for your attention, and we will meet again next week. So actually, currently, I'm not sure if we will have in-person lectures again, or if we stick to online classes. So this will be decided probably this afternoon, where we have the crisis task force will meet again. I'm also a member of this task force, and I think that will be decided. But you will get the information if the classes will be online or in person. Okay, so then there's not a lot more for me as to wish you already a nice weekend and see you again next week. Goodbye.